Hello, good morning. So today we're going to be looking at the very special number e, which was named after Leonard Euler, a mathematician in the 1700s who is considered to this day to still be, if not the greatest, definitely one of the greatest mathematicians in the history of humankind. So he has all sorts of amazing problems he contributed. If you're interested in graph theory or networking, go check out the 7 bridges problem. Or it might be 5 bridges, but either way, Euler was a tremendous mathematician who contributed a lot. Even late in life, he was insanely prolific with how many papers he produced, and he actually went blind about halfway through his life, and he still contributed even more than he was doing before because he I think he even phrased it, I lost the distraction of the visual field. So really, really interesting guy. But he discovered or introduced this number back in the early 1700s from actually the idea of compound interest and increasing the frequency and taking the limit of that behavior. And we'll take a look at how that works in a bit. But for now, you can just think of e as being this number. It's kind of like pi. They call it a transcendental number, which means that it kind of goes beyond what we can do in algebra. So a transcendental number. And that number is around 2.718, and it's a non-terminating decimal. So it's somewhere between 2 and 3. It's closer to 3 than it is to 2. And what happens is this comes up as a really important base in exponential functions, things that compound continuously. And we'll look at that. So we'll look at a few examples of what functions with a base of e look like. What this k means here, you might see that. You might see the connection to that ab to the t already here. Continuous versus annual rates of growth. How do these things compare? And then we'll look at e's origin. It came from a compound interest problem, and so we'll see exactly where that emanated from. And then how to compare effective rates if I have something that compounds quarterly or weekly or annually and now continuously, meaning it never stops compounding. How do we compare apples to apples again like we did last time? So we'll do a few examples and have some fun. Okay, so to start off, I'm actually going to mix up the order here and go to where e comes from. So where e comes from is from a compound interest problem. And what the question was if I take $1 and invest it into an account with 100% interest, but it's compounded not weekly, not quarterly, not monthly, but we want to leave it in the general form, but n times per year. And so if we set this up, how would this look? We'd take $1. Right, well let's go back to our initial formula, right? So we're being super clear. So P equals, right, A 1 plus R over N to the NT, or we could call this P naught, whatever you're comfortable with. That initial investment, this comes from 4.4, our compounding interest section. So, and this is for 1 year. So our P naught is 1 for $1, 1 plus the rate, which we could say is 100% over n, and we're leaving that in the general form, and then all raised to the n power times 1 for 1 year. And so really this 1 is kind of unnecessary out front, so we're really just looking at the quantity 1 plus 100% over n to the nth power. And we're curious at what would happen if we let n go to infinity. right? What did we see last time? We saw that the higher the frequency of compounding, the faster that thing's going to grow, that account's going to grow, right? Or that population's going to grow, because we're allowing that interest to be put back into the account, which helps the growth because exponential functions grow proportionally to how much you have in the account. If there's more in the account, it's going to grow faster. So what if we never stopped compounding and we let n go to infinity? What would this look like? And so one way you can do this is to approximate it with a table. And so what you can do is plug this into your x, or not x1, your x and your y1 in your graphing calculator. And you can put in 1 plus 1 over x to the x. And again, we're going to switch out the 100% for its decimal equivalent, which is 1. And start to input in some values here and see what happens as you let x go to infinity. So in other words, let x be 10 times per year, 100 times per year, 1,000 times per year. Maybe try 10,000. It might break your calculator, honestly. Or you can try, actually you could probably get some more room on that. Try 30,000 times a year. And then there are 31 million. This is how many seconds there are in a year. Let's say if we did it every second. What is this multiplier going to approach? And what you see is it will quickly approach 2.718, which is the number e. So I encourage you not to just take the passive approach. Do this in your calculator because you got to show your brain what's happening for it to make sense. But as we let n, or the x here, the number of compoundings increase, this thing approaches this number. And as we get further and further, we let x be bigger and bigger, it converges, as we say in math, to this irrational number e. It's kind of like pi, right? It sits outside of algebra as its own entity. And it turns out it's hugely helpful in calculus because it's much, much simpler to work with than any other sort of exponential base. So we can convert back and forth. So that's what makes this really nice. So essentially this is the problem that generated E. And it is a question that a freshman in high school could come up with, right? When we're learning about compounding interest and the different frequencies, the logical next question is, well, what if we never stop doing that, right? I could see a kid coming up with that. And so if we never stop doing it, this is what would happen. We'd end up with E, this 2.718 ... as our base. So this is where E comes from, and now we're going to put it into context, look at its graph. How do we map back and forth between the normal exponential function that we've been working with annual compounding versus continuous compounding, and a lot of other stuff. So functions that have a base E, since E is 2.718-ish, it's going to live, its natural graph will live between the 2 to the t curve and the 3 to the t curve, right? If they're all passing through this point with the initial value 0a, then it will stay between these two curves. And we do a little bit more of this exploration in calculus, which is fun, but just to kind of get a sense of where it's at, right? 10 to the t would be a much steeper curve over here. And so it lives between these two things. Now, the idea is that it's nicer to represent some things with base E, and there are places where E is the appropriate base because it's a continuous growth, right? So it never stops compounding. So things that act like that are typically biological, things that are always kind of growing. There is no stop end date, or when we go ahead and accumulate the growth, it's always happening. So things like the spread of disease, a population growing, continuously compounded interest. These are phenomena that are best modeled by E. But there's also times where we want to go back and forth. So if I have something in base E, but it doesn't quite match up to the data I have or the account that I have, what can I do to bend it back and forth to maybe make it fit the graph that I want it to, or the shape of the data that I want it to. And we do that by changing the power of it. So here's it in its natural state, a e to the t. But if we looked at it in the form of, right, here's our normal ab to the t versus a times e to the kt. This k is what I'm talking about. This is an exponent that we can shift on the base e, and if we shift it up, it will make it bend faster, and if we shift it down, it will make it decay. So here's what we want to do. We'll say k equals 0 implies growth. K less than 0 implies decay. And let's look at a graph and see how this works. So if you want to pull out Desmos or your TI-84, and you can kind of play along. Okay, so let's say, for example, I'm just throwing out a random exponential function. Let's say I have this 5 times 1.25 to the t. So this might be something I put $5 into some account and it's growing 25% per year. But I'd rather represent this with an e to some k, because again, e is just in general a nicer function to work with, which you will see later, but we need to start practicing this now. So the question is, what value of k would take me there? So here's just our regular e to the 5 times e to the k, where k is 1, which means it's at that 2.718 growth rate here. And so how do I get it down to 1.25? Well, I'm going to have to mess with this k value here. And we see it's going to be positive, but smaller than 1, right? Because 1 would be 100% growth. But it's going to be bigger than 0.1. It's going to be less than 0.3, right? Somewhere in here, maybe something like 0.23, 0.22. Noticing it's a little bit slower than annual growth of 25% here, that we could consider this to be 22% continuous growth, and it's pretty darn close. Which makes sense that this would be smaller, right, than your annual growth rate. Your annual growth rate, we're waiting to compound all that growth or all that interest until the end of the year, whereas with this model, we're doing it instantaneously, right? As that n went to infinity, we're doing it all the time. So it makes sense that the growth would have to be a smaller rate because it's happening at a faster period of time. So it's catching up quicker. So this is always going to be the case. To get equivalent growths, k will always be smaller than your annual rate if you're comparing the same starting points, right? But let's see what would happen. Let's say I had a decay function. Right, what would we have to do? If I had a 0.8, that's a 20% decay curve, and I wanted to see what base e exponential function would work for that. Well, we said before, if k is less than 0, it'll be decay, right? Which makes sense. If it's just above 0, then this whole thing is a positive. It's a growth factor that's bigger than 1, which means it's going to be growing. If k was 0, what happens? Well, what's e to the 0 power? Anything with 0 power is 1, so this is just going to be a constant function, right? And then if I let k be negative, we see it starts to dip into decay, which makes sense. E to a negative power is going to result in something being less than 1. And so just like we'd expect there to be a difference between the continuous growth rate and the annual growth rate, right here it's just the flip where it needs to compensate a little bit more for that decay. So it's around 0.22 in the negative compared to a 20% decay rate here. So this is something that you can play around with, and again I'll link this calculator in the video notes. So let's see how this continuous growth rate might work in practice. So if we have a medicine that sits in the bloodstream but is continuously being filtered out through the kidneys at a rate of about 8.5% per hour, how much is left after a 250 milligram dose was ingested and we waited 6 hours, right? So how much can we expect at that kind of like halfway through the day? How much of this medicine's actually in your system? So this 250 milligram dose, what does this mean to me? This is the initial dosage, right? That initial starting amount. So if I know that this is a exponential decay function, or Q equals A times B to the T, or A equals E to the KT, because I know this is continuous rate, I know it's going to be this one, then what that tells me is that my K is decaying not the K is decaying, but the quantity is decaying, so K must be negative. And it's 8.5% every hour continuously, so this means that K is going to be negative 0.085. We'll put it in decimal form, and you note that we're putting that sign in there of negative 0.085, and we said the initial value was 250 milligrams, so that's my A. E to the negative 0.085. All to the T, we're looking for the value after 6 hours. So that's going to be all to the 6th power. And so we can calculate that. Let's pull up this guy here. Okay, there we go. 250 times E to the negative 0.085. We can put the X up here, that's fine. We get 153.47 milligrams left in the bloodstream. After 6 hours. Oh, let's get rid of that. So this is how we'd use K. Since we noticed that it was decay, it's going to be negative. What that value is, we put it in decimal form and attach a sign to it. So this is different with the B equals 1 plus R kind of system of finding your growth factor based on the rate. Here the rate kind of sits up in E's exponent, and that becomes that continuous decay rate. Now what I want to do is compare effective rates between maybe an annual rate and a continuous growth rate and see what comes from that comparison. So let's say I invested in an account that earns 5.6% continuously compounded interest. What is the effective rate for an annual compounding interest? So this is where we kind of draw the similarity between A, B to the T and A, E, K to the T. And so what we see is really the magic lies in this multiplier here, right? So if B equals E to the K, and I know that my continuous growth rate is 5.6, that tells me that K equals 0.056 in the positive. So this is really E to the 0.056 equals this B value that I'm looking for. Right, and why do I want B? Well, B is that growth factor, and from there I can determine what the annual rate would look like. So we pull up, all right, what's E to the 0.056? E to the 0.056. This is equal to b, and so that b is 1.0576. And so what does that tell me about the effective annual rate? Well, we know that b equals 1 plus r, where r is that annual growth rate. So then we know that this must be equal to 1 plus 0.0576. So then r must be 5.76% annual interest. Okay, again, why are they different? One is compounding continuously, and the other is compounding at the end of every year. So, of course, the one that has infinitely frequent compounding is going to need a lesser rate to get to the same place that an account earning interest just and compounding it once per year would need. So K will always be smaller than R when you're comparing growth rates from the same starting point, right? So this is how we can kind of find the effective annual rate, or the APR or APY, if we're given continuously compounded interest. Now, to go the other way around, if you're going to try to find the continuous rate given the annual rate, you actually can't do this using algebra or anything like we've done here. It's not that simple. You'd need to use logarithms, which is our next unit, the inverse two exponents. It's that same issue of solving for the input, right? So in other words, if I was to say, find the K such that it has, 8% annual interest. So find K, what is the continuous growth rate that gets us 1.08? Well, here what are we doing? We're trying to solve for the input of an exponential function, that exponent. We can't do this algebraically, so we need to do graphically. Or wait until we have logarithms. Okay, so I wouldn't want you to be using this now in this unit or on this test, but you'd be able to solve this graphically, right? You can plot in e to the x and find where it hits 1.08 and get a graphical approximation. Okay, so the last thing I want to do is work through an example through building a formula again and noting the differences between the different types of functions. So if we started with a town that had population 3,000 in the year t equals 0, again, just our starting point, I know our initial value here, is 3,000. Our starting input must be t equals 0. We want to find a formula for p, the population of the town, if it grows in these different situations, so with these different rates. So the first one is if it grows by 200 people per year. So you got to ask yourself, what type of growth is that? Is that exponential? No, right? How do we describe exponential growth? It grows based on how much you have. This is what we call a flat rate of increase, right? Or a constant rate of change. What reminds us of constant rates of change? This is a linear function, right? This is a linear function. So this should be of the form p equals b plus mt, where b is your initial value and m is your rate of change. So this would be 3,000 plus my rate of change, or my slope, is 200 times t. All right, so this is my m equals. Only because it's a flat amount, right? That it's 200 every single year. It's not increasing because now there's more people in the town, which would be more closely aligned to exponential growth. So how about if it grew by 6% per year? What would that look like? This is exponential growth, right? Why? Because it's proportional to how much you have. So starting at 3,000 people and increasing by 6% per year, that's an exponential relationship. And since it's every year, we can use our AB to the t form, where A is your initial value, which we know is 3,000. B is our growth factor, which is 1.06 because of that 6%, all to the t. And so that's an exponential function that we've worked with before, annual growth. And if we switched it up and said, well, maybe they were growing at a rate of 6% continuously per year, which can often be the case, then what does this look like? Well, continuous growth is given by a e to the kt. So that'd be 3,000 e to the 0.06 t. And so these all describe different towns with different rates, and you can see hopefully the difference between the formulas here. But also want us to get used to substituting for that rate. K and R and B all act pretty differently, even though they're so closely related, right? But they will change the structure of a formula. They are different types of parameters, and they'll change the graph and all that stuff. So this is the last worked example I wanted to do, so let's make sure that we've got everything that we wanted to do here. So we looked at E's origin, where it comes from, in compound interest with the limit of 100% divided into n compoundings per year. If we do that infinitely many times, we end up at 2.718, which is just kind of crazy that it just lands on this number, right? We've looked at functions that have a base e, what their structure is, right? A e to the kt as compared to a times b to the t, or a times 1 plus r to the t. We looked at continuous versus annual rates, and we looked at how to compare effective rates for something that's given with either compound interest or continuously compounding interest or continuously compounding decay. So you'll notice it's kind of wordy. We have to throw in that word continuous if we're talking about E, because otherwise it's uncertain how frequently we're compounding. So that's Euler's number. Again, you don't really have your head around, and I'm saying this because I haven't told you this because you haven't taken calculus yet, you don't quite have your head around how important this number really is. It takes getting to what we call differentiation, or finding the rate of change at an instant where we see E really shines and this AB to the T is kind of not so great, not so nice to work with. So after we study logarithms, we'll be able to solve for K and be able to then convert any exponential function into this form, which is really, really powerful. So I hope you have fun playing with this new number. Take some time to just look at graphs, play with the sliders, get comfortable with the structure of this thing and the shape of its graph, and then again converting back and forth, and bring all those great questions into the class discussion. Remember that if you have textbook problem practice that isn't going great, or you're stuck on a couple, that's the place, is in the class discussion. So if you leave a comment on your assignment, I'll certainly be reading those, but I'm much more active in the class discussion. I grade every couple days. So, all right, I will see you guys there. Have fun. Enjoy.